Hi students, welcome to Jce eConnect. We are discussing subject basic electronics and we are into module 4, the last part of the module 4. Theoretical part already covered in previous 7 lectures. Today we are dealing with the lecture 8 of this module and we are going to solve the numericals on the various theoretical concepts that we have studied in this module. So we'll start with the first numerical in this module 4. That is, you can see here in this particular circuit, it is a circuit of transistor amplifier or BJT as an amplifier, and it is asked to determine the voltage gain and the AC input voltage for this particular circuit, and it is given that RE is equal to 50 ohm or RE dash is equal to 50 ohm they have given, RC equal to 10 kilo ohm is given, and the input is 10 millivolt. For this you have to determine what is the voltage gain and the AC output voltage. Now how to determine the voltage gain of the transistor amplifier? We know that the formula for the voltage gain of the BJT amplifier is given by RC divided by RE dash. So here both the values are given. RC is 10 kilo ohm, RE dash is 50 ohm. So 10 kilo ohm divided by 50. If you substitute that, you will get the, it is 1 kilo ohm, 1 kilo ohm divided by 50. RC value is not 10 kilo ohm, 1 kilo ohm. So 1 kilo ohm divided by 50, you will get the voltage gain of the BJT amplifier as 20. Now we know that the voltage gain AV can also be written as the output voltage by the input voltage, because basically gain is the ratio of output voltage by input voltage. So that is, the output voltage divided by input voltage is the gain. So from this we can write output voltage is equal to gain times the input. Right, so input is given as 100 millivolt and the gain we have determined is 20. So 20 into 100 millivolt, we get the output as 2 volt, and that is what is asked to determine the gain. Gain we got 20, and then the gain into input gives you the output. So output here is 2 volt. So this is how a simple example on BJT amplifier we can solve. So the important thing that you should remember here is this formula. RC by RE dash is the gain, and the gain can also be written as output voltage by input voltage. That is VC by VB can be the gain. From that we can determine this. Similarly, as a homework you can try here, what will be the value of RC when we want to have a gain of 50. So for the same circuit, if you want to have gain equal to 50, what should be the value of RC that you have to find? So again, how you can find that? Use the same formula, RC by RE. AV equal to RC by RE. AV is given to 50, RE dash is already given to 50, you will get the RC from that. That is how you can solve that next part of this particular example. Now we'll go to the second example. Again, similar example, a simple one. Determine the voltage gain and the AC output voltage for the circuit shown considering the value of RE dash is equal to 50 ohm and RC equal to 2 kilo ohm. There is no difference between the previous example and this example. Almost everything is same, only values, one or two values are different. So same formula you can use again here. AV is equal to RC by RE dash. So here RC is 2 kilo ohm, RE dash is 50. So now the gain you get here is 40. RC by RE dash 2 kilo ohm by 50 gives you 40, and then the output voltage is given by V out is equal to AV into V in or AV into VB. So VB given here is 200 millivolts. So 40 into 200 millivolts, that gives the answer as 8 volts. So same example again, the formula as I said, RC divided by RE dash. That is the formula we have to use here also. We'll move on to the next example. Right. This is the third example. You can see here. Again, very simple example. Determine the value of the RC for the circuit shown below if the voltage gain is if the voltage gain is 80 and RE dash is equal to 50 ohm. Voltage gain is 80 and RE dash is equal to 50 ohm. So how you find this? Again, AV is equal to RC by RE dash. So here AV is given as 50, RE dash is given as 50, you have to find RC. So RC is equal to again 50 into 50, and that is equal to 2500 ohms or 2.5 kilo ohms. Right, again here also the formula what we have used is AV is equal to RC by RE dash, which we have derived in the first part of this module 4 when we have studied about BJT as an amplifier. Right, now the next one more example is shown there, that is a transistor amplifier as a voltage gain of 50. What is the output voltage when the input voltage is 100 millivolts? So far input was given and they were asked to find you the output. Here output is given, gain is given, you have to find the input. Again the formula is gain is equal to output by input. So what is input then? Output divided by gain. Gain is output by input, so input is given, gain is given, we have to find output. So output is equal to AV into VI, sorry, it is they are asked to find the output voltage when the input voltage is given. So V0 is equal to AV into VI, that is equal to 5 volts. So other way, if they give, say like in the same example, they could ask like this: determine the input required to produce the output of 5 volt from a transistor amplifier having a gain of 50. How you can solve this? Same formula you should use. AV is equal to V0 by VI, and from that substitute the given values and get the input required to produce that particular output. That is how we can solve the example on the transistor amplifier. Now we'll solve the next example, which is on transistor as a switch. So you can see the circuit there, and what is the question asked? For the circuit shown below, what is the value of VCE? VCE means what? The collector emitter voltage, that is this voltage. What is the value of VCE when the input is 0? When there is no input applied, what is the value of VCE? That is what the first thing you have to find. Then the second part, what you have to find is what is the minimum value of IB required to keep BJT in saturation if the transistor beta or beta DC is equal to 200, right? And then the third part is calculate the maximum value of RB when input is 5 volt. So here there are 3 different things you have to find. First you have to find what is the value of VCE when there is no input applied. That is the first thing. Then second thing what you need to find is what is the minimum value of base current IB to keep the transistor into saturation. That means when the transistor is on, what should be the value of IB required when the value of beta is equal to 200. They have given the value of beta. That's what you have to find. And in the third part, we have to find what value of RB required to when the input is 5 volt. What is the maximum value of RB required when the input applied is 5 volt. That is what you have to find here. The 3 important things that you have to find from this particular example. And if you observe this particular circuit, it is a case of what? Transistor as a switch. So one by one you can find the required things. The first case, when Vin is 0, when you consider the first case, when input is 0, the transistor is off. The transistor is in cutoff. As a result, it will not conduct any current and the current IC becomes 0. And since the current IC becomes 0, the voltage VCE will be equal to VCC. So in the first part, when the input is 0, VCE equal to VCC, and that is equal to whatever the VCC given, that will be equal to the output, right? That is equal to 20 volt. VCC equal to 20, sorry, VCC equal to 10, so VCE is also equal to 10 volts, right? The first example is over. VCE is equal to 10 volt because VCC is 10. Now the second part, they have asked to determine what is the minimum value of IB required to keep the transistor in saturation. That is, you need to find IB mean, right? So to find IB mean, first we need to find IC sat, saturation voltage, saturation current. How do we find IC sat? It is VCC minus VCE sat divided by RC. VCC minus VCE sat divided by RC. From this you can get the IC sat. So what is the value of VCE sat? VCE sat is not given, so we'll assume it as 0. So when VCE sat is 0, IC sat is equal to VCC by RC. VCC is how much? 10. RC is how much? 1 kilo ohm. So 10 by 1 kilo ohm is equal to 10 milliampere. So we get IC sat is equal to 10 milliampere. If IC sat is 10 milliampere, now easily we can determine what is the minimum base current IB required. So what is the relationship between IC and IB? We know that IC is equal to beta times IB. Since IC is beta times IB, now we can write IB is equal to IC by beta. We have determined IC. How much we got IC? That is 10 milliampere. That is IC sat. And what is the value of beta given? Beta is 200. So if you substitute IC is equal to 10 milliampere, beta is equal to 200, we get the value of IB mean as 50 microampere. From this you can see that the base current IB is very small. So we got the IB mean required for this particular circuit is 50 milliamperes. That is the second part of this particular numerical. Now what is the third part? Third part of this numerical, they have asked you to find the maximum value of RB if the input applied is 5 volt. If the input is 5 volt, what is the value of what? RB. Now how do we find that? We can apply KVL to the input side. When we apply KVL to the input side, we can write it as minus V in plus IB into RB plus VB equal to 0, because we'll come across 3 voltages here. The input voltage drop across RB and the voltage drop across base emitter junction. So we can write that KVL equation as V in equal to IB into RB plus VB, or minus V in plus IB into RB plus VB equal to 0. So from that we can write the equation for RB as, or RB max as, RB equal to V in minus VBE by IB mean. RB max is equal to VBE, RB max equal to, V in minus VBE by IB mean. V in is how much given? 5. Then VBE we can consider normally it as 0.7 volt, or sometimes it is considered like 0.3 also, but if it is silicon we take it as 0.7. So 5 minus 0.7 divided by 50 microampere. If you substitute these values, you will get 5 minus 0.7 divided by 50 into 10 to the power minus 6. So if you simplify this, you will get the value of RC required as 86 kilo ohms. Right? This is a very good example on transistor as a switch. So what you can see here is, important thing is you should know how to apply KVL at the input and output. By applying KVL at the output, you can get VC equation very easily, and by applying KVL at the input, you can get the IB or RB equation. And if you want to relate input current with the output current, you have to use the current relationship between the base current and the collector current, that is collector current IC as beta times IB. That is about the example on transistor as a switch. Now there is one more example shown here. It is mentioned the LED used requires 30 milliampere to emit sufficient level of light. Determine the amplitude of square wave input necessary to make sure that the transistor is in saturation state. Use double the minimum value of base current required to ensure saturation, and also assume VC is at equal to 0.3 volt. Again, it is given, it is the case of same transistor as a switch to turn on and off the LED, right? So how do we go ahead with this particular example? First, again, we need to find what is IC sat, right? So how do you find IC sat? IC sat is equal to VCE minus VCC minus VCE sat by RC. You can see here IC sat is equal to VCC minus VCE sat by RC, right? So if I substitute that, it can be shown that IC sat is around 32.3 milliamperes. So once you get IC sat, then we can get IB mean. How do you get IB mean? IB mean is equal to IC sat by RC. So if you substitute the values of IC sat what you have got, and if you substitute the value of beta, the value of beta also is mentioned here in the circuit, that is 50. So if I substitute that, we get the base current IB as 646 microamperes, right? But they have mentioned that to ensure transistor acts in saturation, consider the value of IB as 2 times the IB mean. So if I take IB which is equal to 2 times of IB mean, it becomes 2 times of 646 microamperes. So it becomes IB is equal to 1.29 milliamperes, 2 times of that. Now using that IB equal to 2 times IB mean, now if I apply KVL to the input, we can easily find what is the minimum input required. So input required can be calculated. Vin is equal to IB into RB plus VBE. Vin is equal to IB into RB plus VBE. Substitute the values of VBE, that is given as 0.7 volt. Then Vin we can obtain by using the value of IB which we obtained in the previous case, and the value of Vin becomes 4.96 volt. So again, it's all about applying KVL to the input or to the output and relating input and output by using the current relationship IC is equal to beta times IB. That is one example on transistor as a switch to drive LED, right? We'll move forward. Like there is a next example shown there, which is very simple again, which is on transistor amplifier. In fact, to achieve output of 10 volt with an input of 30 millivolt, what voltage gain is required, which I already told to you. Like now output is given, right, and input is also given. You have to find the gain. The gain is what? V0 by Vin or Vc by Vb. Substitute 10 by 300 millivolt, you will get a gain as 33.33. That is about transistor as an amplifier and transistor as a switch. Now we'll move on and we'll try to solve a few examples on feedback amplifiers. Now the first example on the feedback amplifier is given here. You can see there. Calculate the gain of the negative feedback amplifier having open loop gain A equal to 2000, and if the feedback factor is 20%, right, it is given A is equal to 2000 and beta is 20%, means 0.2. You have to find AF, right? So what is the gain of a negative feedback amplifier with feedback? AF equal to A by 1 plus A beta. So A is 2000 and beta is 0.2. Substitute this, you will get the gain as 4.98. So you can see from this example that the negative feedback decreases the gain. The original gain without feedback was 2000, and with negative feedback of 20%, we are reducing the gain to only around 5, that is 4.98. That is a simple example on negative feedback amplifier. We'll see one more example. It is given again on negative feedback, that is gain sensitivity. An amplifier without feedback has a voltage gain of 2000. If the gain changes by 20% due to the variation in the temperature, find the change in the gain with the feedback if the feedback fraction beta is equal to 0.1, right? So what is given here? It is given that open loop gain A is equal to 2000. Then it is also given beta is equal to 0.1%, and it is something mentioned. What is this 20%? It is the rate of change of gain with respect to open loop gain A, that is dA by A is 20%, means dA by A is equal to 0.2. So if you recall, we have derived one important relationship. The change in the gain with feedback is equal to change in the gain without feedback into 1 by 1 plus A beta. That is, change in the gain with feedback decreases by a factor of 1 plus A beta. So if you use that formula, DAF by AF equal to 1 by 1 plus A beta into DA by A. So how do we get DAF by AF then? Substitute 1 by 1 plus A beta and DA by A. DA by A is given, that is 0.2. Then 1 divided by 1 plus beta is 0.1 and A is 2000. So if you substitute all, you will get it as DAF by AF as 0.000995, and if you want to express it in percentage, then this becomes DAF by AF is equal to 0.0995 percentage. That is how we can determine the change in the gain with feedback. Right. Then there is a next example. Again, it is a similar example. The gain factor is in a feedback. The gain factors in a feedback amplifier are A equal to 5 into 10 to the power 5 and AF equal to 1000. That is, open loop gain is 5 into 10 to the power 5 and closed loop gain or gain with feedback is 100. The parameters AF must not change. The parameter AF must not change more than plus or minus 0.001%. It should not change more than 0.001% due to change in A. What is the maximum allowable variation in A? So A given, AF given, DAF by AF is given. Now it is opposite to the previous example, and you have to find what is DA by A. So for that we should find first beta. Beta is not given directly. A and AF is given, so easily we can get the beta using the formula AF equal to A by 1 plus A beta. So AF equal to A by 1 plus beta. From that we will get beta equal to 0.009998 or beta is equal to 0.9948 percentage. Now the formula what we have is DAF by AF is 1 by 1 plus A beta into DA by A. So substitute the values given. DAF by AF is 0.001. Directly you can substitute in percentage itself and get in percentage. That is DA by AF is this. Then 1 by 1 plus A into beta into DA by A. So if you rearrange the term, you will get DA by A is equal to 5%. That is, the allowable change is 5%. Again, here in these two examples, previous example and this example, the important formula that you should remember is, first is AF by A by 1 plus A beta, and next is DAF by AF equal to 1 by 1 plus A beta into DA by A. Right. So that is about the feedback amplifier. Now next we'll move on to the last part, next part of this particular module, that is the oscillators. We'll solve one example each on RC phase shift oscillator and the wind bridge oscillator. So here in this example, what is asked? Design a RC phase shift oscillator for a frequency of 1 kilohertz. Only this is the statement given. Now when they say design, normally we have to draw the circuit to be designed, and then we have to think like what are circuit elements present in that circuit, and you have to find the values of all those circuit elements. Now when we talk about the RC phase shift oscillator, we know that the frequency of oscillation F0 is given by 1 by 2 pi root 6 into RC. F0 is equal to 1 by 2 pi root 6 into RC. Right. So if you see is, to get the frequency, we need to find the values of R and C. So we have a single equation and there are two unknowns, R and C. Right. So how to solve this? At least we have two equations, then we can solve and get the correct values for R and C. But since they are asked you to design, in such cases, we need to assume one value and we have to find the corresponding value of the other parameter. So here what we do is we'll assume C. Let us assume that C is equal to 0.1 microfarad and F0 is given as 1 kilohertz. So we'll substitute both the values in this equation. So when we do that, we get R value as 650 ohm, because 1 by 2 pi root 6 into RC, F is 1 kilohertz, C is 0.1 microfarad, and then we got R is equal to 650 ohms. Now if you recall the circuit of RC phase shift oscillator, there is one more resistor present there, that is the feedback resistance RF. So you have to find the value of that also, because basically there are three components, RF, R and C. So already you have found the values of R and C. Now you have to find the value of RF. So for that, how do we find that? We know that in RC phase shift oscillation, the gain should be greater than 29 because feedback fraction is 1 by 29. So RF by R, that is the gain, should be greater than 29. Hence RF equal to 29 into R. So R value you have got, that is 650. Substitute, you will get RF should be equal to, minimum value of RF is 18.85, and since it should be greater, you can select any value, but minimum value required is 18.85 kilo ohm. So here I have shown you can select RF equal to 21 kilo ohm, that is a standard value. Hence the designed values are R equal to 650, RF equal to 21 kilo ohm, and C is equal to 0.1 microfarad. So this is how we can solve the numerical on RC phase shift oscillator. So quickly we'll see one example on Wien bridge oscillator 2. So you can see the circuit of the Wien bridge oscillator given there, and it is given that R1 equal to R2 equal to 61 kilo ohm, C1 equal to C2 equal to 0.001 microfarad, R3 is equal to 300 kilo ohm, and R4 equal to 1000 kilo ohm. 1001 kilo ohm, R4 equal to 100 ohm. Now how do we determine the RC values for frequency of oscillation of 10 kilohertz? It is given that R1 equal to R2 equal to R, then frequency of oscillation for Wien bridge oscillator is given by F equal to 1 by 2 pi RC, right? So substituting the values, given values first, we'll get F equal to 2.6 kilohertz. That is the first part over. Now in the second part, they ask you to determine the values of RC to get a frequency of 10 kilohertz. So again here, how do you get that second part? F naught is 1 by 2 pi RC. F is given or F naught is given, and you have to find the values of R and C. So now both the values we can't find using the single equation. So what you do? We have to assume again one value. So I'll assume let R equal to 100 kilo ohm, then F naught is 1 by 2 pi RC, C is 1 by 2 pi F naught into R, and then C becomes 0.159 nanofarad. So this is how we can solve this. Again, what is important here is you should know the frequency of oscillation of this RC oscillator. For Wien bridge oscillator, it is 1 by 2 pi root 6 into RC, and for Wien bridge oscillator it is 1 by 2 pi RC, and for RC phase shift oscillator it is 1 by 2 pi root 6 into RC, right? One more example is shown here. Find the value of R and C for an audio frequency of 1 kilohertz in RC phase shift oscillator. Again same, assume C and find the value of R, because formula is 1 by 2 pi root 6 into RC. C is 0.1 microfarad. Substitute, you will get R is equal to 645.74 ohms, right? Now we'll see one last example on oscillator using 555 timer, or stable multivibrator using 555 timer. So it is given a 555 timer is connected as a stable multivibrator with R1 equal to R2 equal to 7.5 kilo ohm, C equal to 0.1 microfarad, VCC equal to 5 volt. Calculate the frequency of oscillation and also sketch the voltage waveform. Now R1, R2, C, VCC is given, so easily we can determine the frequency of oscillation, that is F. Directly we can use the formula, or we can find T by finding T on and T off, and then we can get the reciprocal. Directly also you can do by using the formula of frequency of oscillation, right? So T on is given by 0.693 into R1 plus R2 into C. Substitute the values, you will get T1 is equal to 1.04 millisecond. Then T off is 0.693 into R2 into C, so T off is 0.52 millisecond. So when you add T on plus T off, you will get T, and that is T is 1.56 milliseconds. So once you get T, F is 1 by T, that is frequency is reciprocal of time, so you will get F as 640 Hertz. And then the output waveforms and the capacitor waveform. Output waveform you can see here is the square wave with on time equal to 1.04 millisecond and off time equal to 0.52 millisecond. Then you may ask, if the formula is available, why we have to find this and then get the frequency? Since they are asked to draw the waveform also, it is must to find T on and T off. So it is better to get T on, T off, T and then frequencies, so that easily you can draw the waveforms too, right? And then you can see here 2/3 of VCC and 1/3 of VCC, how much you will get, that also you need to calculate, so that you can get this sawtooth kind of signal, that is the capacitor voltage, right? So one more example, direct how we can make use of the formula of frequency of oscillation is shown here, like previous example only, where we obtained T on, T off, T and then F. So directly also it is possible to find F. A 555 timer is connected in a stable multivibrator mode with a frequency of 400 kilohertz. Calculate the value of C if R1 equal to R2 equal to 8 kilo ohm, right? So here F is given, R1 is given, R2 is given, you have to find the value of C. So easily you can get from that. Frequency of oscillation is given by 1.44 divided by R1 plus 2R2 into C. Therefore C is equal to 1.44 divided by F into R1 plus 2R2. So substitute the values of R1, R2 and F, you will get C is equal to 0.15 nanofarad. That is how we can determine the capacitance C required to get a frequency of 400 kilohertz from the values of R1 and R2, which is equal to 8 kilo ohms, right? And then to conclude, I'll be giving one simple, very simple example which can be solved in just 2 lines, which you need to do it as a homework. Find the charging and discharging time of the 0.5 microfarad capacitor shown in this particular circuit. If you see the circuit, it is a case of a stable multivibrator with R1 equal to 10 kilo ohm, R2 equal to 5 kilo ohm and C equal to 0.5 microfarad. Instead of giving the values of R1, R2, C, it is given in the form of circuit, and they ask you to find charging and discharging time of the capacitor. That means you have to find T on and T off. So how do you find T on? By using the formula 0.693 into R1 plus R2 into C, and T off 0.693 into R2 into C. This is R1, this is R2, this is C. All the 3 values are given, so easily you can get, so you can do that as a homework. So these are the few numerical examples that I have discussed on this module 4. So of course the numericals cannot just be explained by putting the problem statement as well as the solution on the slides like what I have done in this particular video. Alright, so actually whatever the examples I have explained, I hope all of you will be going through this video. So my request is just go through the video once, right, and then try to copy the problem statement, and you should solve that numerical on your own. That is how you can learn the numericals. Of course, to cross check your answers, then you can go back to the video once again and you can verify your answers, right? So with this completely we have covered the entire syllabus of module 4, including theoretical aspects, numerical aspects. So dear students, if you have any queries in this module 4, it is a very important and very easy module of your syllabus, and important from your examination point of view also. So you go through all the 8 video lectures, and if you have any difficulties, any queries, always you can contact me, right? Okay, thank you very much.